Hey everyone, welcome back to the JNTUX concepts. So in our previous video we have covered uncertainty principle and wave particle duality. So as moving forward we are going to discuss classical versus quantum mechanics, a theoretical comparison of both classical and quantum mechanics. This particular topic we are going to discuss in this particular video. So before starting the topic, don't forget to hit the subscribe button and do like this video. If you are new to this channel, don't forget to watch the playlist for computer networks and protocols, artificial intelligence. So do check out those videos and yeah, don't forget to subscribe. So let's get into the topic. Classical versus quantum mechanics. So in our previous videos, we have discussed that what is meant by classical mechanics, what is meant by quantum mechanics, what it covers in the physics, and what quantum mechanics covers in the physics, what are the scopes, etc. So in this video also we are going to have a brief definition of what are they. That is what is meant by classical mechanics and what is meant by quantum mechanics. So it's going to be a theoretical comparison as in the syllabus by JNTUA they have given particularly that a theoretical comparison. So before directly moving into the topic, I'll be giving you a comprehensive definition of what is meant by classical mechanics and what is meant by quantum mechanics. So let's start with quantum mechanics. Quantum mechanics is a branch of physics that deals with the motion of macroscopic objects under influence of forces based on laws that are formulated by Newton, Hamilton, etc. scientists. It assumes that objects have definite positions, velocities, and momentum at all the times. So classical mechanics is a deterministic framework, or you can say in a way that classical mechanics follows a deterministic framework. It means it does have some accurate and possible or definite outcomes which we can assume. Moving to quantum mechanics. Quantum mechanics is a branch of physics that deals with the behavior of microscopic objects like matter and energy at atomic and subatomic levels. Here, the physical state of a system is represented by wave functions. The outcome of observations or measurements are not deterministic in quantum mechanics, whereas quantum mechanics follows a probabilistic framework, or you can say the outcomes are probabilistic instead of deterministic. So, as we have read the definition of classical mechanics, it states that classical mechanics is a deterministic framework. That means the outcomes are definite. But whereas coming to the quantum mechanics, it follows a different framework, that is a probabilistic framework. Here you cannot have a particular definite outcome. The outcome depends on the measurement or the observations made by the observer. So it gives a probability of possible outcomes. I hope you have understood the definitions of both classical and quantum mechanics. So let's get into the comparison or differences in simple way. So classical mechanics and quantum mechanics are two distinct frameworks as they fundamentally differ in their assumptions, mathematical formulations, and interpretations of nature. In classical mechanics, the objects have definite positions and velocities at all the times, so that the state of a system can be precisely predicted using Newton laws. We know that it is deterministic, so using the initial conditions, the future behavior is uniquely determined. That is nothing but the deterministic framework of classical mechanics. So with the initial conditions, the future behavior is uniquely determined. But whereas in quantum mechanics, a particle does not have a definite position or momentum until it is measured. So as I have explained you during the definition part, the same is being repeated here. It is described by a wave function which gives the probability distribution over all the possible outcomes. So as I said, in classical mechanics, the outcome or a future behavior is uniquely determined by the given initial conditions. But whereas in quantum mechanics, a particle does not have a definite position until it is measured. It gives a probability of all possible outcomes. So that is the first difference or a first comparison between classical and quantum mechanics. In second point, classical mechanics relies on continuous variables and smooth trajectories. It obeys the determinism principles and locality. But in quantum mechanics, it uses a discrete quantized energy levels and operates in probabilistic framework, which is governed by Hilbert space and Schrodinger equation. And quantum systems exhibit superposition, entanglement, and non-locality, such fundamental principles. So moving to the third point, in classical mechanics, position, momentum, energy, etc. observables have definite values at all the times, and measurements reveal pre-existing values without disturbing the system. So it is an important point for classical mechanics. But whereas in quantum mechanics, the observables correspond to operators on the state space. Here a measurement outcome are eigenvalues, and the act of measurement or observation affects the system. So it means when an observable component like position, momentum in classical mechanics is measured, it just reveals the a pre-existing value without disturbing the entire system. But when the same done in the quantum mechanics, it responds in a different way. The outcomes in quantum mechanics are eigenvalues, that is a real number and a imaginary number. And the act of measurement itself or the act of observation itself disturbs the entire system. It changes the system. So that is the summary of this third point. So moving to the fourth point, classical mechanics aligns with everyday experiences, but whereas quantum mechanics often requires abstract mathematical tools and accepting of unknown fundamentals. Classical mechanics is applied in our day-to-day life, but quantum mechanics is not so often related to our day-to-day life. Classical mechanics adheres to local realism, assuming that objects are only influenced by their surroundings. But quantum mechanics or systems defy this through entanglement and non-local interactions. In quantum mechanics, the particles follow the local realism, that is nothing but the objects are assumed to be influenced by their surroundings. But in quantum mechanics, this particular phenomena or this particular concept is completely rejected, as we know that we have discussed what is meant by entanglement and what is meant by wave particle duality and non-local interactions. So in that same way, quantum mechanics or the systems or the qubits follow the entanglement so that they can have non-local interactions. Despite all the differences, classical mechanics is actually a limiting case of quantum mechanics. At large scale or high quantum numbers, the quantum mechanics reduces to classical mechanics because quantum affects the negligible. The classical mechanics provides accurate predictions in everyday scenario but fails in microscopic scales. The classical mechanics provides accurate predictions in everyday scenario but fails in microscopic scales, where quantum mechanics can accurately describe those microscopic things. So that is all about the differences or the comparison of classical mechanics and quantum mechanics. And there is an important point which you can write and highlight in your exam. The classical mechanics can simply say as the special case of quantum mechanics. It can also be asked in your, there is a chance of being asked this particular point in 2 marks question. So do note this point, and that is all about classical mechanics versus quantum mechanics, a theoretical comparison. So in our next video, we'll be covering the next topic in the syllabus. So till now we have covered a good amount of topics in introduction to quantum technology and applications. I hope you have understood this concept, that is a theoretical comparison. So that's it for this video. Keep learning.